Good morning. This is an assembly video just to give some of the options and the background to the latest of the desk fans that I've done. We're going to be looking into this. I'm going to explain how to put it together and some of the options that you've got, because a few people had said that they wanted to see that. And we're also going to talk about why this is probably the best one. If you're going to print any of the fans I've done, this is probably the one that you should use. This fan is all about this bit. We'll talk about that in a second. This is the core of it, though. This is the core of the fan, and this is the reason why this is probably the one that works. This is a normal desktop PC fan, 120 millimeters. This is a reasonably thick, powerful one, but you know, you can get anything you like. There's various different types. We're going to put this aside for a minute, because actually that's not the main reason why this was fanned is existing. As with all of the fans I've done, there's an aerospace link with the fan, and this, in this case, is the aerospace link. This is the bit that gives me the aerospaciness. This is a corner cascade assembly. Corner cascades are something that you get in wind tunnels. It's these parts here, the horizontal parts. Their job is to turn the flow from this direction, going straight up, here, out horizontally. The idea is that what happens is that these little veins are aligned towards the flow vertically here, and they're aligned horizontally here, and they help the flow go around the corner in a very ordered, very consistent way. Most wind tunnels are, certainly the big ones, have some kind of bend in it, even if it's only one or two. Many of them go round in a complete circle, and when you have those corners, the flow isn't going to want to go around it uniformly. It's going to want to get all piled up. The bits in the middle are going to get stirred up. And the idea behind this is that it will make it much, much smoother. And these can be very efficient, very low loss if you design them properly. This one, probably not so much. But the idea is that this makes it very uniform, which makes the tunnel much more effective because the flow is smoother, but they also mean that it uses less power. And some big wind tunnels can be terrifyingly high power, megawatt level. So any losses are really going to be noticeable. So this is the aerospace link, and the idea is that this sits on here and orients the flow from vertically with the fan to horizontally, which is more what you need. And there's a little bit of an angle. I don't know whether you can see it, but there's a little bit of an angle on the stand in order to make it a little bit easier to deal with. So this is the aerospace link. These verticals here are really just to allow it to print more successfully. And this prints without support. In a couple of cases, there's built-in support. This is a fairly long print. It's not a difficult print if you have reasonable part cooling. But the idea behind this is that it is effectively a single piece that does all of the bits. So this is the aerospace link. Put that aside. This is the main bit of the fan, and this really talks about the first parts that you need to have a think about when you're deciding what it is that you want to make. This is the intake. This is something that you'll need. It prints that way. And this is one of the bits where you will need reasonable part cooling. This is a reasonably substantial overhang, so you will need to have decent part cooling if that's not going to droop. It should print without supports, though. This is just the PC fan. I say it's nominally 12 volts. This box is something we'll talk about in a minute, which is the way that you can control the voltage. But this is your first decision. You have two options. You can have this part, which is a very simple sort of bullet fairing shim that would fit here on top of the fan, and that would go here. And the idea is that this is intended just to smooth out the flow a little bit behind the fan, because there's a big center section of the fan, and this makes it a little bit smoother. Is it worth it? I'd say probably not. I didn't notice any big differences. This one's the one that you should probably print. It's bigger, but it is a lot more effective, and I'll explain why. These are flow straightening vanes. Effectively what happens is that as the flow comes out of the fan, it's not just going vertically, it's spinning. And these veins sit in that flow, and they try to straighten it out. And there was a surprising amount of swirl that came out of these, out of the fan. Really quite surprising, and that even made it through here. It wasn't a problem. It definitely worked. You could definitely print that bit, and one of the nozzles, and you're going to have something that works very effectively. But what I found was, as the flow was coming out, when it had a lot of swirl, spinning meant that it would spread out a lot more. And with this, the flow is much more concentrated, which means you can have it further away, which can sometimes be useful. So I liked this. I think this is probably the one that you should print. And again, prints without any kind of support. There's some overhangs here, but they're pretty moderate. So in terms of assembly, this is the next thing that you would do. You put that on there, and it gives you this assembly. And then you have another part, which is this. This is literally just a duct, and that fits on here and produces the next part of the fan. We'll leave that aside for the second. We'll take a brief detour into the control. Now, to begin with, the first version, I had this little box, and literally all this had within it was a little DC to DC converter. One of the ones where you can control the output voltage with a little screw on a multi-turn potentiometer. That worked pretty well, but it meant that I had to have it set where I wanted it, close it up, and then more or less leave it. I did drill this hole in the top so I could turn the screw from the outside, but broadly though, if you wanted it faster, you had to get the screwdriver out, which was a pain. The next bit I experimented with was this, which is where I was using a motor controller on an Arduino Uno, and this is an Arduino motor shield. What you can see in there is a DC-DC converter. The power supply input, I've got a socket around here. This is designed to take a 19 volt power supply, and that's a bit too high for this. So I knock it down to, I forget what it was, about 14 volts, I think. I knock it down to about 14 volts so that it's closer to what this is happy to accept without me cutting the supply between this and the Arduino. There's a jumper that you can cut in order to make it deal with more or less whatever voltage you like, but I didn't want to do that. And then this is just a little switch. It's actually a clicky keyboard switch. I quite like these, make a nice noise. And this just literally is pulled to ground, and that just signals to the Arduino that it should be changing the speed. So that's really all this is just something where this powers the fan, but it also powers the Arduino, and you're able to have the two things. It's as you can see, it's convenient, but it's pretty bulky. It's not the world's nicest thing. So that's that bit. I'm now going to go and attempt to put some of these bits together so that you can see the final layout. Okay, with that jump cut out of the way, I've done a little bit of screwing the parts together. It's not completely installed, it's very much still got bits hanging out of it, but I just wanted to show. So that bit gets screwed in there, this bit, that bit, this bit's a bit awkward, but at least it's possible, and like that direction that's there. As with most of the things that I do, these are held together by tapping the holes in here for M3. I use a spiral flute tap, which is able to go through the plastic without any trouble with simply finger pressure. And the idea is that you can ream this to 3mm so the screw goes straight through. You can ream this to 2.5mm and then tap, and the screw will hold in it perfectly for the level of torque that we need. This is the outlet. As you can see, it's not particularly smooth on the inside, but this is where it starts, and it works like this. The flow will come out and it's fine. However, you have a choice at this stage. You have some things that you can print. Now, this is my experimental nozzle. This is the nozzle that's probably the one that's easiest to deal with. This one model needs to be updated because, as you can see, you can see daylight through it because the overhang was far too much and the model was far too thin. This one looks kind of funky. Again, there was a trying to do something vaguely aerospace-y. There are some old aircraft engine nozzles that look sort of like that. I wouldn't recommend that one. I'm not even sure I'm going to upload the model. This is the one that you should probably get. And so you install the nozzle on and you have that there. So this is basically the assembly of the fan. You have the choice of how you do the electronics. If you have a 12 volt supply, you can connect it into the motor. If you wanted to power it with USB, you're going to have to do a bit of testing. Some of these PC fans will start on 5 volts. Nearly all of them will spin on 5 volts. They won't all start spinning on 5 volts. So USB would be handy because everybody's got USB power supplies hanging around. You could power it with a battery bank and so on. But it may not work. So it's worth testing with your fan to find out whether it spins, and if it does spin on 5 volts, whether it gives you enough. So that's the end of this bit of the video. We're now going to take a bit of a detour and go to talk about the rest of the fans that I've done over what is many years now. So this is the first of the fans that I did. It's this was many years ago. This was something that at the time I called the most useless desk fan in the world, and I'll explain a little reason why. I wanted to have a fan that was a bit smoother than the ones that you get as just desk fans. They have blades, the blades spin, you get a lot of buffeting. I didn't really like that. I also wanted something that was vaguely aerospace themed. And I liked the idea of having something that had a compressor instead of just fan blades. It's the same kind of thing as these Dyson ones, which they call bladeless. They do have blades, they're just internal, they're not really big ones. So I made this. As you can see, the printing is not the world's best quality. This was printed on my old Delta printer, and the complicated Delta kinematic didn't fit very well with the low-powered Arduino, and so you got a lot of skips and pauses, and the quality's rubbish. There's also a huge print. This one, it worked very well in terms of flow. The outlet's here. It's a bit broken now, but the outlet's here. I'll show you the inside in a second. It produced a really beautifully smooth flow, but if you look at the inside of it, and I really should have hoovered this. This has been upstairs for a long time. Oh, look at the dust. Anyway, this is a lovely compressor wheel that I printed. It is all OpenSCAD. It's quite a complex model. It's probably one of the more complex OpenSCAD models I've done. And I don't know whether you can count, but there's 6 main blades and 12 smaller blades. And that's the problem, because if you look in here, these are the stators, these little things shaped like wings, and they are 6. There's 6 of those. And I don't know whether you're aware, but one of the problems is, what that means is every time this thing turns by a 1/12 of a revolution, there's going to be a little pulse of noise from all 6 of these. And as a result, this was really noisy. I even noticed this just before I printed it, and I thought, it can't be that loud, it's not spinning very fast. I was wrong. It's super loud, really annoying. As a result, I never really ran this for very long, and you can see this is where the motor mount was. The motor was a desk fan motor. It's a shaded pole AC induction motor, and went through there, mounted here, a little bit of space for the coil there. The idea was that would then run, and why would you not use a fan from a desk fan? Of course, what that meant was that I was taking a fan that was perfectly functional and replacing it with one that was really loud and annoying, hence one of the most useless fans in the world. This was so offensive that I didn't really run it for very long. It looked fairly decent, it looked interesting, but I didn't really run it for a long time. It was too annoying. So we move on to the next one, version 2. Jump cut to version 2. This isn't complete, I haven't got all the parts. It had a compressor similar to this, slightly smaller. Inside here, again, you can see from the casing, it's the same kind of thing. Beautiful print quality on the top there. This had a problem. Version 2 had a big problem in that the version 1 had been so offensively noisy that I'd never run it for very long. And I changed this one, so you can see here there are 5 status. There were 11 blades, so I removed it so there were 11 blades, and the compressor fitted in here. This isn't the right one, but it was the same kind of size. It fitted in here, and so it would pull the air in and fling it out, and it would come out to here, and it would then come out around the casing. But the first one was so offensively loud I never really ran it for more than a few seconds. This one was really quiet. It was effectively silent. It was incredible how much of a difference just one blade and one stator removal made. The only problem was that I hadn't realised how incredibly hot shaded pole induction motors get. And you can't really see. You kind of can a little bit if the light catches it, but can you see there's a little shiny spot there? The problem was these are just PLA, and PLA goes rubbery above 60 degrees Celsius, and it got really hot and it got rubbery and it melted. So this one was actually the early part of the early one of the designs. I replaced this with one with vents that I can't find. I don't know where I've put it. Probably thrown it away because it was awful. The other one had vents, knacker ducts. The knacker ducts are a particular type of very aerospace vent. I thought that was really good. This was the top of the motor housing, and again it had lots of holes in it because I needed a lot more motor cooling, and it worked beautifully. It was running really well. It was lovely and cool. It was really nice, but the problem was that it ran beautifully while it was on. There was plenty of cooling. It didn't all melty, but as soon as I switched it off, the big heavy motor made these go rubbery. The weight meant it sagged, and then the compressor started scraping on the inside. That's what this blue stuff was. This was me attempting to work out where is it scraping, how can I remove the scrapiness, before I realised that the problem was the motor. So that one also, living up to its useless forebears, was not a particularly successful fan. So another cut, and we'll go to version 3? Version 3 I think we're up to now. Version 3 was the first one that was actually functional. There's a video on this, so I'm not going to go into a huge amount of detail. I'm certainly not going to take it apart. This one worked. The outlets here, you can see I've learned lots of motor cooling. The intakes here, it's designed so that you can't get your fingers in because the rotor, again, it's not there, but it would be right inside there. And in here was the motor housing, and the motor housing was to have a brushless DC motor. This was where the speed controller was. I reused it for a later one, so it's not there anymore. But this worked really well. Bit noisy though, quite loud. It was. I used a drone motor. I used a drone motor and speed controller, and I think it runs at a kind of offensive frequency. I could tolerate it, but the family, who all have better high frequency hearing than I, didn't really like it. And the idea was that it would eject the flow out here, and it would try and entrain a little bit more in here. I don't think it works very much, but it looked pretty interesting. It looked pretty funky, and it does actually work. If you're not bothered about the noise, if you want it for somewhere where it's a bit loud anyway, you could absolutely make this. You might have a bit of trouble getting hold of the motor or speed controllers, but people have printed it. It does work. I'm not sure I'd recommend it, but it can be done. So, but it was pretty complicated. It's a big print. I wanted to go to something else. So we're going to go on to the next version, but this is not one that you'll see a video or even files for, because I just didn't really think it was worth doing. So we'll have another jump cut to get to the next one. This one's a lot bigger. Very different design to the others. All of the others had a kind of 3D compressor where it's pulling flow in, spinning out, but there's a lot of movement through it. This is a much simpler compressor, and I wanted to do it so that it was much easier to balance, and you can see it just in there. It's a very flat compressor. I experimented with that with this. It's basically the same as that. This is actually the motor from another computer fan, which has been cut out and mangled and turned into a driver for that to experiment. It doesn't work that well, but it showed that this worked perfectly. And the idea is this again, it just spins this way, it grabs the flow, flings it outwards, and produces movement from the air. and that's all in there. And the idea is it takes the flow into here, flings it outwards, and it goes through here. Inside there you see tiny, actually can you see? I don't know whether you can see. Let's see if I can get an angle. Yeah, you can maybe just see little tiny corner cascades. The same as the other one, only really tiny. And this was designed to refer a little bit back to one of Whittle's early turbofans, where the intake and the go into the combustion chambers kind of looked a little bit like that. Does it work? Yeah. Is it good? Not really. This is the control box. Variable speeds, again, the nice clicky keyboard switches. It does work. It is a fan. Doesn't work that well. I wasn't convinced that this was actually worth releasing. It turned out to be, although it was supposed to be a simpler print, it turned out to be a relatively complex print, and I just thought it probably wasn't worth releasing. So like all of the rest of them now, having made this video, this is going to get dismantled. So those were all of the different fans. This is a complete saga of what I've done. Aerospacey themes obviously work reasonably well for a desk fan, but overall, although I originally wanted to have something where I was printing the spinny bits that try and actually make the flow work, although I wanted to do that, I've since come to the conclusion that it's probably not worth it. And broadly, I've come back onto the idea that actually just using the PC fan is a good way to do it. This worked really well. It's nice and controllable. This was probably not that safe. This did spin pretty quick. Running these brushless DC motors and the controllers off like a laptop power supply isn't the best idea. It doesn't work that well. But the idea was effectively this gives you something that produces a fan-like effect, and it looks quite interesting, and it's a little less boring than a standard desk fan. So overall, as a summary, if you're gonna print these, if you fancy having a go, don't print the first one. Don't print the second one, because even if they're there, I would say they're terrible. The third one, maybe. This one isn't released, so you can't. If you're going to print one, do the one that's made with a PC fan, and it's much better. We are going to have another little cut, though, because I do want to talk about something very briefly around the control of the PC fans with Arduinos. So back to the whatever version this was, 5, 4, depends how you count. These motor controllers work really well. They're basically something that designed to allow you to drive a motor in either direction under the control of an Arduino. The problem is the way they produce the variable voltages is with chopping, pulse width modulation. So if you want a tiny voltage, it produces a really small pulse of a higher voltage, and if you want the full voltage, it just does it has it on all the time. Problem is the default pulse width modulation speed of an Arduino is about 490 Hertz, which means that at any power other than full, it whines really loudly at 490 Hertz. And that's just not something that I was able to deal with. It is absolutely possible to change that pulse width modulation frequency. You can do it. It works very well. There's just a command. It's just a little copy and paste thing. The one thing I found, though, was I actually then had to change the timer code, because when it does the timers are, what you're doing is changing the timer code to change the pulse width modulation speed, which meant that when I was debouncing the switch, so if I was setting up so that it wasn't detecting like 5 presses every time I pressed it, I had to change the timer code to suit, because everything was running, not the process of running faster, but all of the events were happening much quicker. So if you're happy with the whining, which you won't be, you can just use it as is. I maybe could have looked to smooth it using capacitors or something, but it was easier just to change it. So this now has, I think it's like a 32 kilohertz pulse width modulation rate, and it's inaudible. At least it's inaudible to me. My hearing is not as good at the high frequencies as it used to be. Maybe some people could hear it, but I certainly can't. So this is it. This is the one that I'd recommend. This is flexible. Just using a DC-DC converter is absolutely possible. If you're going to print one, print this one. And have a nice day.